Okay, let's go ahead and get started. Are any of you graduating next week? Oh, congratulations. That's exciting. That's exciting and scary at the same time. Now you're going to have to go out into the big wide world and do other things. Okay, well, we're rooting for you. Today, we're just going to cover two topics that often come up on the MCAT and make sure that you've been exposed to those at some level. And then on Tuesday of next week, I'm just going to work problems, sample problems. You know, I'm going to try to take it from each of the topics that we've covered since the last exam, and hopefully help us get ready for that last exam. Yes, it is. Yes, indeed. And it's on the homework that's due next Tuesday. And there are questions from this material on that practice exam that's online. Yeah. Questions before we begin? I spoke to Clark yesterday. He was, I woke him up, so he's kind of groggy, but he seemed in good spirits. Today, they're doing all the mapping of his brain so that they know which part controls which muscles, and then tomorrow morning they will do the operation. So if you don't mind, I'm going to offer the prayer this morning. Dear kind Heavenly Father, we are filled with gratitude for the many blessings that we have received at thy hand, for the opportunities that have been afforded us, for the blessings that come to us through our families, through our loved ones. And we ask, Father, a special blessing this day upon Clark and upon his loved ones, that they might be comforted and that they might be buoyed up as they go through this difficult time. We ask a special blessing upon those that will be performing the operation and assisting those individuals, that they might be blessed with alertness and with those skills that they need to do their very best. We ask now, Father, as we prepare to finish our studies in this semester, that we might be able to keep track of all the ideas and concepts that we have learned, that we might be able to feel comfortable with the information. We ask a special blessing upon these young people as they make so many decisions, as they face so many challenges, that they might be helped in their path. And these things we ask, Father, in the name of Jesus Christ. Amen. Okay. We need to finish up our discussion of relativity. We left off with this. He was trying to get you to move, right? So we left off with this weirdest of the effects, the relativity of simultaneity. The fact that two events can be simultaneous in one frame, but not in another. And that's going to be the case if those two events are separated by some distance L in the rest frame of the clocks. Now, the reason for that, we said, was just the fact that, well, how do you get your clocks synchronized? Well, one way would be to flash a bulb in the middle of, say this is a train, and the clock on the right is at the front of the train, the one on the left is at the back of the train. Well, I just put a flash bulb in the middle of the train and flash it. And when that light reaches the clocks, they turn on and the reading starts from 0. But if I look at that from the sidewalk frame, what I see is that the light goes out at 3 times 10 to the 8th meter per second. That's the same in every frame. But now the distance that that light has to travel to get to the trailing clock is shorter than the distance that it has to travel to get to the leading clock, because those clocks have moved as the light pulse was traveling. And so that means this trailing clock is going to turn on first. Okay, by the time this leading clock reads 0, this one already reads something bigger than 0. Or if, you know, if this read 0, this would read something negative. It hasn't turned on yet. Okay. And this is the amount by which that difference occurs. In other words, that's the time difference measured in the sidewalk frame. Okay, that's how much the trailing clock is going to lead the leading clock in the sidewalk frame, if they're synchronized in the moving frame. Now, there's an example in the textbook that is just, I think, the most beautiful example in the whole book. And as I told you before, my co-author Ron Hellings, he is one of the leading general relativists of his time when he was alive, and he passed away a couple of years ago. He wrote this example, and of course he's got Gunslinger Greg and Rawhide Ron having a shootout on the Einstein Express, which is traveling at 3/5 the speed of light. This is a very fast train. And it's got glass sides because why wouldn't it? Okay, so school marm Sue is at the platform. She's a sidewalk frame. And through the glass, she sees that Greg fires his gun in this shootout from the back of the train when Sue's clock reads 0 seconds, noon, high noon. And then she finds that at 40 nanoseconds after noon, as she looks through the glass, she sees Ron fire. And so they both are wounded. They're both, you know, taken to the hospital. But then the sheriff gets involved. And it turns out that the law says that the sheriff can only hang one of these dirty bums. Okay, the one that shot first. Okay, the other one was just firing in self-defense. So the question is, who shot first? Well, in the platform frame, the sidewalk frame, clearly Gunslinger Greg shot first. But schoolmarm and the sheriff was going to hang Greg. But then schoolmarm Sue said, wait a minute, I understand special relativity because I read the textbook, and I know that there's going to be a time delay in my frame of reference, just because those clocks are moving and they're separated by a distance. And so the sheriff goes onto the train. He measures the distance between the two clocks, front of the train, back of the train, to be 30 meters. And Sue uses this formula here to get a time delay of 60 nanoseconds. 60 nanoseconds. Now, what does that mean? Well, that means that when she saw this happen, if Greg's clock, if he had one, was reading 0, when Sue looked at this clock over here, it would read something less than 0. And the delta T prime was 60 nanoseconds. And so if this clock was reading 0 at this time, Ron's would read negative 60 nanoseconds. Now, let's wait 40 nanoseconds in the platform time, the sidewalk time, to when she sees Ron fire. Well, that's 40 nanoseconds in the sidewalk frame. But the clocks that are in the train, they're moving slow, okay? They're moving slow according to the platform frame. And so while 40 nanoseconds take place on the sidewalk, only 0.8 times that, or 32 nanoseconds, take place on the train, because the relativistic factor is 0.8 for that speed, okay? So that means that when if Greg fired at t equals 0, Ron fired at t equals negative 28 nanoseconds. And so indeed, rotten rawhide Ron fired first and needed to be hanged. Now, I need to point out that it may take you a few readings of this example to wrap your head around all of those different pieces. I would encourage you to do so. And then I would also encourage you to be careful as you read the paragraph after that example. And that's because there's a mistake in it, okay? In the paragraph that comes right after this example, Greg and Ron are switched, okay? The names are switched, and instead of Ron firing first, it was Greg firing first. Instead of Ron being at the front of the train, it was Greg being at the front of the train. And I discovered this error in the book shortly after my friend passed away. A day after I sang at his funeral. And it's important to me because it told me that in the original example, I was the bad guy. I shot first. I was the one that needed to be hanged. But Ron, my friend, wasn't willing to go to print with his friend being the bad guy. And so at the last minute, he switched us and put him at the front of the train. But he forgot to change it in the paragraph that came after. And so for me, it was a testament of our friendship. When he was a bishop of the YSA ward in Bozeman, I was his first counselor. And when I was the branch president up in a little branch up in the mountains near Yellowstone, he was my first counselor. And so we served for a long time together. That's not going to be on the exam. Okay, so these are the three strange effects that happen. Lengths contract, time dilates, and simultaneity is lost. Okay. Now, these weirdnesses bring about some paradoxes. You may have heard of some of these paradoxes. The most famous of them is the twin paradox. You have two identical twins, Alice and Betty, but they have different skills. Alice grows up to be an astronomer, while Betty trains to become an astronaut. They have the same interest, however. When Alice discovers evidence that one of the planets near Alpha Centauri, the nearest star system to our own, has conditions suitable for life, Betty is chosen to fly in a spaceship and visit Alpha Centauri system to investigate further. The spaceship is launched on the twins' 30th birthday, and soon Betty is flying towards Alpha Centauri, which is 4 light years away from Earth. A light year is how far light can travel in one whole year. At a speed of 4/5 the speed of light. When she finally arrives at the planet, she discovers that although it has conditions suitable for life, no life actually exists on that barren surface. It's boring, so she turns around and comes back at 4/5 the speed of light. Now, this is what it looks like if I plot distance versus time in years, and this is in light years. We see that Alice, the astronomer, stays home. And in her frame, it took 5 years for Betty to get to that planet, because she's going four light years at a speed of 4/5 the speed of light. And so it takes 5 years. However, we remember that Betty is traveling at 4/5 the speed of light. So her clock runs slow, including her biological clock, her aging clock. And so as she makes this path, this trip to the planet that takes 5 years, according to her sister, it's only going to take 3 years in her clock that is her body, okay? And so she's only going to see 3 years expire and another 3 years. And so that means that she's going to come back 36 years old. But her sister Alice is now 40 years old. That doesn't seem fair. And it also doesn't agree with the first postulate of relativity. And that is that for any two inertial reference frames, everything should work out the same. I shouldn't be able to tell one from the other. And the key to this paradox is that the two frames are not inertial. Alice's is, she's just sitting in her lab, looking through her telescope, okay? But Betty is accelerating to get up to the speed of 4/5 the speed of light. She's accelerating to turn around to come home and get back up to 4/5 the speed of light. She's accelerating to slow down from 4/5 the speed of light to stop. Now, in addition to the special theory of relativity, which Einstein gave us in 1905, he also created a general theory of relativity, which, you know, when I was your age and I was an undergraduate here at BYU, I had the misconception that there were only 5 people on the planet that really understood Newton's or Einstein's general theory of relativity, and I found that I'm way wrong there. It's more like 36 people. Okay, so it turns out that general theory of relativity predicts the aging that would happen to Betty during those accelerations. And it turns out to be exactly the 4 years that we're missing. Okay, so Einstein once again wins out. Okay, how many of you have heard of the photoelectric effect? Okay. The photoelectric effect is something that we can demonstrate here. I've got here an electroscope that we talked about earlier in the semester. And you remember this just measures when there's charge present. If I charge up this plate here, remember the circle's it's just to hold things in place. The electroscope is this plate connected to this bar and this little smaller bar that's free to rotate on a pivot. Now, I'm just going to polish this plate real quick to get rid of any oxidation. Okay. And then I'm going to charge the electroscope, and I could have done that with a charged rod, but instead I'm just going to hook it to a battery, and I'm going to put an excess of electrons on there. Okay, so I've got way too many electrons on there, and because those electrons want to be as far apart from each other as possible, that's forced this little pivoting rod to be as far as it can get away from the vertical rod. Everyone see what's going on there? There's too many electrons. Now, what they found back in 1887, and this was done by Hertz, is that if you shine light on this plate, if it's the kind of light that you can easily see, visible light, you can make that light just as intense as you want, and it is not going to affect those electrons on the electroscope at all. And you know, they experimented with all sorts of intensity, very high intensity. Now, this was puzzling to them back then because they felt that if you gave those electrons enough energy that they could jump off of the plate, that they would leave, okay? And the more intense the light, the more energy is in the beam. And so if I have a strong enough beam and I blast that plate for a long enough time, the electrons should get enough energy to just pop off, okay? But they don't. But we also find that if we take ultraviolet light, and you remember ultraviolet light is on the energetic side of that electromagnetic spectrum, okay? That's what's going to give you a sunburn, that ultraviolet light. And so it has more energy. And so if I, let's see, where's my button? There's my button. Okay, so if I shine ultraviolet light on that, is that plugged in? Okay, that will sometimes happen. Okay, so this is old and this sometimes sticks. So let me start once again. And I was warned about that. It shocks me. Okay. So now it looks like it's moving freely. And so if I shine ultraviolet light on there, I get absolutely nothing. Well, that's just not, that was working just a moment ago. Okay, let's try it again. Oh, huh. There's this on switch. Let's use the on switch, people, should we? Okay. You're going to tell your grandkids about that. Okay, now I hit that and I can tell it's working because it's vibrating. And you see what's happening to the, well, the people behind me can't. See that went down. Those are that I was blocking. Talk to your neighbor, they'll tell you. Okay. Well, that is still going on. Okay, I learned something there. There's an on switch. Okay, so they were able to demonstrate that those were electrons that were flying off of the plate using a magnetic field and looking at the way that they rotated. And they used different target materials, different metals for the plate, and they changed the wavelength and intensity of the incident light. Okay. Now, what they found was that if you vary the wavelength and intensity, that electrons were sometimes ejected from the material, but not always. And we also could apply a voltage difference across from the plate, the target plate and the collector plate. And if we essentially make that voltage a voltage that would fight the electrons, that would slow the electrons down, if I made that voltage big enough, I could stop all of the electrons that jumped off of the plate. And so what they looked at was, how big do I have to make that voltage to get all of the electrons to stop getting to the collector plate? And that gave them an idea of how energetic the electrons were when they popped off of that target metal, okay? How much energy they had, because that's gonna, more energy is gonna require more voltage to get them to stop, right? Okay. Now they used a current meter, an ammeter, to measure how many electrons are being collected in that collector plate. Now, what they found was troubling, and that is that, well, this part wasn't troubling. This part made sense. If they had higher intensity, they were getting more electrons popping off. But when they looked at the voltage that it took to stop even the most energetic of the electrons, they found that it was totally independent of the light that they were using. If they had a very, very bright light, the electrons still got stopped by the same voltage as if they had a very dim light, okay? And so this is not what classical theory, wave theory, suggested should happen. According to classical wave physics, they should have different stopping voltages. Now, more intense waves have more amplitude and therefore more energy, so you would expect that they would give more energy to the electrons, and you would expect that the electrons would require more voltage if they had more energy. But that didn't happen. Now, the classical theory, this is just to kind of review, said that the energy of the light, the intensity, was proportional to the amplitude squared. And the experiment disagreed with the classical theory because the shutoff voltage was independent of intensity. That's just what we saw in the previous slide. A bigger amplitude should represent more energy and give me more collected electrons, but the experiment says no. The photoelectrons are emitted instantaneously. As soon as I turn on that ultraviolet light, I start getting electrons popping off, as I would see in the ammeter. But it should, by the classical theory, require those electrons to save up the energy until they had enough energy to pop off of the plate. So the fact that the maximum amount of kinetic energy, which we can measure by just looking at how much voltage it took to shut off the flow, was independent of the intensity, but depended on the frequency of the light. The high frequency light, ultraviolet, was able to do it, but the low frequency light, visible, was not able to do it, okay? Now, so it turns out that Robert A. Millikan, how many of you heard of Robert Millikan? Okay, Millikan did the oil drop experiment that measured the charge to mass ratio of an electron. If you'll believe it. But that's not what happened, okay? What happened was that a good Mormon boy, a good Mormon boy, Harvey Fletcher, was a grad student of Millikan. And Harvey Fletcher did the experiment that found that ratio of the charge to the mass of the electron as part of his thesis defense. And then there was some wheeling and dealing where Millikan said, you need to give me credit for that. You need to make me the first author on that paper. Otherwise, I don't think you're going to get your degree. That sounds pretty slimy. right? Yeah, so anyway, we're gonna call this Millikan's contribution, but I don't think so. Millikan set out to prove that Einstein was wrong, just like a lot of people have tried. And he wound up proving him correct. And what we see here is that if we look at light from different frequencies, this is getting more and more energetic, higher and higher frequency. Or we could also think of this as lower, smaller wavelength. So what he found was that the voltage required to stop those electrons got smaller and smaller as the frequency got smaller and smaller. And so when it went to zero, he looked at this value here and tried to interpret what that meant. And we'll do the same. But the fact that there was a cutoff with frequency suggested that instead of a wave that was just basking these electrons with energy, kind of like laying on the beach and getting your sunburn, okay, that instead this energy was delivered by particles, by bullets that were each individually hitting an electron and giving all of its energy to that electron, okay? And so, and that's what Einstein suggested to explain the photoelectric effect. He suggested that maybe the light that's hitting that plate is particles, Okay, so Einstein's theory was that light comes in individual bundles or light quanta that we now call photons, and that the energy of each photon is this constant called Planck's constant times the frequency of the light. Now, Planck's constant, it turns out, is this number here that I don't want you to memorize. That's not going to be useful, but it is one of the big constants in physics. But there's a more useful form of it that I'll show you in just a moment. Now, what Einstein said was that each photon comes in with this much energy. And when it hits an electron, it gives that much energy to that individual electron. It gives up all of its energy to that electron. But he also said those electrons aren't free to just jump off of the plate of metal, or they would be doing that. He said there's a work function. That's this symbol here. And that work function is different for different metals. And what it represents, that work function represents how hard it is for an electron to get off of that metal. How hard the rest of the metal surface is trying to hold on to that electron. And that's different for gold than it is for silver, than it is for copper, than it is for other metals, okay? And so this work function is defined as the least amount of energy it would take for an electron to escape that metal, okay? You know that some of the electrons that are hit by a photon are deeper in the metal, and it's going to take them more energy to get to the surface and then pop out. But if I look at the electrons that come off of this plate with the very most kinetic energy, they're the ones that were right at the surface to begin with, and they had the easiest time getting off the metal, okay? Now this energy, this work function, is usually a couple of what we call electron volts. And Clark talked to you about electron volts when he gave his lecture. Now, what did others think of Einstein's idea? Well, Planck, the one who this Planck's constant is named after, he wrote a letter of recommend for Einstein to get a job. Can you imagine that? Needing to write a letter of recommend for Einstein. Yeah, let him in, let him in. But in that letter, Planck kind of slaps Einstein by saying that he, Einstein, may have sometimes missed the target in his speculations, as in his hypothesis of light quanta cannot really be held too much against him. He did other things which were good. Well, it turns out that the one Nobel Prize that Einstein received, he deserved 3, but the one that he did receive was due to his explanation of the photoelectric effect. So Planck, who was killing him with faint praise here, was wrong. Okay, was wrong. Okay, so if we look at these, again, these are plots of frequency versus the voltage to stop the most energetic electrons. And you see that each of these metals has a cutoff frequency, a lowest frequency below which you can't get any of the electrons to jump off the metal. And so if we want to know what the work function is for a potassium surface, we want to look at this one right here. And we notice that the cutoff frequency is about 5.4 times 10 to the 14 hertz. Okay, that'd be the minimum frequency that's going to give enough energy to the electron to escape the metal. Okay, now if we find that energy related to that frequency, we take that Planck's constant, we multiply by that minimum frequency, and we get this amount of energy. 3.59 times 10 to the minus 19 joules. But again, when you're dealing with electrons, joules is just not the right unit. That's a good unit for us, how many joules of energy you expend as you walk to school, but not for an electron. And so what we do is we divide this joule by, this is the number of electron volts in a joule, and you'll recognize that as the size of an electron charge, okay? And so what we get is 2.24 electron volts. It's just a unit of energy, okay? Now, because this has a cutoff voltage, and when the frequency is this minimum frequency, it doesn't take any voltage to stop them. When those electrons pop off, they're just floating there. You know, they just barely had enough energy to get off the metal and nothing else left over. And so the kinetic energy max is 0. And so if I look at this formula, this minimum amount of energy is the work function. In other words, this cutoff frequency represents just the amount of energy a photon would have to overcome the work function, to give the electron just enough energy to escape, but nothing more, nothing more. And so that's how you find the work function, and you will have to, in your homework, find the work function of a metal. You would take the lowest frequency that would make this happen, or the longest wavelength that it could happen for, and then you would use that to find the energy associated with that cutoff frequency or wavelength, okay? Let's look at an example here. The wavelength associated with the cutoff frequency for silver is 325 nanometers, okay? And because that's the cutoff frequency, that's the lowest frequency, that number there is going to give me the work function for silver, okay? We want to know the maximum kinetic energy that electrons would jump off of that silver plate if they had a higher, a shorter wavelength than that. If their wavelength was only 254 nanometers. Now remember, shorter wavelength means higher frequency, higher energy, higher energy. So this is the amount of, this is going to tell me the amount of energy to get off the silver, and this is going to tell me how much I got left over that's kinetic energy. So I know I've dumped that all on you all at once, but I just want to walk you through it. The work function is given by the energy of that lowest frequency. But we weren't given the lowest frequency. We were given the longest wavelength that would make the electron come off the silver. And so we rewrite this frequency, the minimum frequency, as C over that wavelength. And then we do the same thing with this frequency here. That's the frequency of the photon coming in. That's this wavelength here. Because I don't know the frequency, but I do know the wavelength, I write this as C over lambda. Now, I said there was a better form of Planck's constant. When we're dealing with the photoelectric effect, and indeed a lot of atomic physics, we're rarely dealing with h by its onesies. We're usually dealing with h times the speed of light. And if we take h written in electron volts and we multiply it by the speed of light, what we get is this number that's very, very useful. That's one you should put in your toolbox, is that Hc is 1240 EVs over nanometers. And that's useful because sometimes you know what the energy is in EVs and you're looking for the wavelength in nanometers. And sometimes you know the wavelength in nanometers, but you're looking for the energy in EVs. And so this is the most useful form. And so I can rewrite this equation here. I just replace Hc with this. And now I can plug in my wavelengths and I get that energy, that the maximum energy that it comes off with is 1.066 eV. Okay. Again, very similar to one of your homework problems that will be due on Tuesday. Now, the most useful equation that you can put into your toolbox for this part of the lecture is this one here, okay? This is the amount of energy that the photon gives to the electron. This is the amount of energy that it takes to get off of the metal target plate, okay? So if I give the electron 20 electron volts, but it takes 5 electron volts to get off of that plate, well, I'm only going to have 15 electron volts left to race across to the collector plate, okay? See what that's saying? That's just balancing your checkbook. Now, if I plug in what Hc is, this is the form that you'll be using when you work your homework over and over again, okay? You'll be using that equation there. Check that your neighbor is still awake.
Well, what about it? Oh, what's EV? I just like to know what's EV.
Okay, questions? Let me see if I can make this visual for the visual learners out there. What we've seen so far is that if I send in a wave, but it has a long wavelength, which would be low energy, nothing happens. And I can make that amplitude as big as I like, nothing happens, okay? As long as that wavelength stays long. But if I bring in a short wavelength, high frequency, high energy, as long as I remember to turn on the lamp, when that high energy comes in, let me go back. If I bring in a high frequency, an electron pops off. If I bring in that high frequency at a bigger intensity, I get more than one electron popping off. Now, Einstein would say that bigger intensity just means I got more photons, okay? If I have even a larger frequency, shorter wavelength, what I get is the electrons come off with more energy. Now, the way Einstein sees that is a low energy photon comes in and it sends out an electron with small energy. And if I have two of those low energy photons come off, each one strikes an electron and frees it from the metal. But if I bring in a more energetic photon, one of higher frequency, an ultraviolet one, it sends off an electron with more energy. Let's use a clicker question to see how we're doing. We've seen this plot before. And what it tells us is that as I get to a lower and lower frequency, it takes less and less voltage to stop the electrons from getting to the collector plate. And eventually I get to a cutoff frequency. That frequency is the lowest frequency that will still allow an electron to escape the metal, okay? Now, this is more of a math question than a physics question. You've seen these kind of plots in your math class. The kinetic energy max is this vertical axis. The frequency, F, is this horizontal axis. What's the slope of this line going to be? Which of these over here? I'll get you started. Okay, now you can click. We'll see if we're better at math or at physics here. Okay, last call. Get your attendance points. Good, okay. The slope is indeed Planck's constant, okay? Planck's constant. And I see this from this equation here. Y is equal to mx plus b. You've grown up with that equation, that when we have y and x, y is equal to mx plus b is going to be, that's going to give me a straight line where this is going to be m and that's going to be b. Okay. Now, x is equal to 0, y, yeah, okay. Let's do another one of these. This is fun. What's the work function if I look at that graph? While you're doing that, I'll just point out, this is just trivia, but from that graph, Millikan or Harvey Fletcher whichever you believe did the experiment, was able to measure the value of Planck's constant to within 0.5% of the accepted value today, just by measuring that slope. Okay, so last call. That all of us? Oh, good. The answer here is C. That is, okay, the y-intercept here is down at 1.8 EV. Okay, and since we have a minus sign there, this would be a positive quantity here. Okay, let's turn our attention now to nuclear decay. When Clark was teaching us a couple weeks ago, he taught us about the different types of nuclear decay, alpha decay, beta decay, gamma decay. But what he didn't get to was the rate of decay. And when we talk about the rate of decay, what we typically talk about is the half-life of a decay. And I imagine that you have all encountered this many times in your studies, in your biology classes and other classes. Ultimately, the half-life is the time it takes 1/2 of the nuclei to decay, okay? And so we typically solve for this number m, which is just the time that has elapsed divided by the length of time for one half-life. Okay, so if the half-life is 20 days and I've waited 60 days, this m value would be 3. And then we can say that the number of nuclides, radioactive nuclides, that I still have remaining at time t is going to be equal to how many I started with divided by 2 to the m power. Okay, so n of t is the number of radioactive particles remaining at time t, and n0 is the number of radioactive particles that we started with. Now, as you saw in your reading for today, m doesn't have to be an integer. It turns out that I've got one example in the homework where m is an integer and one where it is not. And again, I'm going to show you some examples to help you work that homework. I'm going to show you one where m is an integer and one where it is not. Okay. Now, carbon dating, it turns out that carbon-14, which is radioactive, is one of the isotopes that Clark taught you about, and the ratio of it to regular carbon, the stable type of carbon, is very, very constant in our atmosphere, okay? And so as we breathe in, we take in carbon-14 and carbon-12 in that ratio that it exists in the atmosphere. And we keep doing that as long as we're breathing. But as soon as we stop breathing, we stop bringing it in from outside. Likewise, plants, you know, they have, as long as they are alive, they are bringing in the same ratio of carbon-14 to carbon-12. But after death, because the carbon-14 is decaying and turning into nitrogen, this ratio changes, and that ratio can tell us the age of the tree or the bone or whatever it is we're trying to date. Now, it turns out that the half-life for carbon-14 is 5,730 years. And as you know, that means that if I start with 100 particles of carbon-14, the radioactive carbon, that after that many years, 5,730, I would have 50 left. But those are still, you know, just carbon-14 atoms. They don't know that, oh man, I've been lucky. They just know they're carbon-14. And so in the next 5,730 years, I only had 50 of those particles left, so half of those are going to decay, and I would be down to 25 particles. And then after another 5,730 years, I would be down to 1/8 or half of 25, 12.5. See if your neighbor thinks that's really, really easy. Was there a problem? Not the first time you've been kicked out, right? Let's be clear. Okay. So with your clicker again, if the number of radioactive nuclides drops by a factor of 8, has 1 half-life path, 2, 3, 4, or 8. If ever there was a time that we were all going to get the right answer, this is really a celebrity Jeopardy question. Can you point to your own head? Okay. If we all get this right, Oliver takes us to Disney World. You worried? Don't be. Okay, last call. Okay. They've got your back, Oliver. They've got your back. The answer is C. Because 8 is 2 to the 3rd power. 1/2 times 1/2 times 1/2 is 1/8. Okay, so the answer is 3 half-lives. Now, when you're dating things, you need to decide what radioactive nuclide you're interested in. This example points that out. In 1991, a German tourist discovered a well-preserved remains of an Iceman trapped in a glacier in the Italian Alps. His possessions and tools were consistent with Bronze Age technology. And so they used carbon-14 to date him rather than carbon-11, which had a half-life of 20 minutes. Why? Because they suspected that 20 minutes just wasn't long enough to get this guy dated, okay? So, first example, this is the easy one. We know that radium-226 decays by emitting an alpha particle. If I start with 1/2 gram of this pure radium, I find that it's emitting 1.83 times 10 to the 10 alpha particles every second. So I've got that many decays a second. The half-life of the decay is 1,600 years. What will be the decay rate of this sample after 4,800 years? And who's going to wait around to measure it to see if we're right? Okay. So let's solve this. The first thing we want to find is this value M, which is how many half-lives does this many years represent? So if I take 4,800 years and divide by the half-life of 1,600 years, I get 3, an integer number. Now, I know that m to the third, I'm sorry, 2 to the third is 8. So that means that I'm going to have 1/8 of my radioactive particles still left over after that many years. Is that much clearer? Here's the new part, okay? As we saw on that graph that we showed a little while earlier, if I've got twice as many particles, my decay rate, the number of decays per second, is going to be twice as big. And so that means that the decay rate is proportional to the number of radioactive particles present. So if the number of particles drops by a factor of 8, if we wait that many years, the decay rate in decays per second drops by a factor of 8 as we wait that many years. Check to see if your neighbor followed that. That's important because in the homework, some of the problems are asking how many particles are going to still be around. And some of the questions are asking, what's the decay rate 20 years from now? Okay, so you have to know that if you know the one, you know the other. Okay, they're proportional. So to find the decay rate, I just take the number of decays I had per second originally and divide by 8. 1/2 times 1/2 times 1/2. Okay. Now, this last example is a little bit more challenging. Free neutrons are unstable and decay by a pathway where a neutron changes itself into a proton and an electron and an antineutrino, but I didn't get the bar over the neutrino there, with a half-life of 881.5 seconds, okay? Suppose we start with 1,000 free neutrons. They're in a bundle, and they're created at the surface of the sun and ejected by a solar prominence erupting, and they head towards the Earth at the speed of 1.69 times 10 to the 8 meters per second, a little more than a half of the speed of light. Okay, everyone see the picture? A bundle of these neutrons are heading our way at half the speed of light. How many of these neutrons are going to still be neutrons by the time it hits the Earth? Okay, and the distance from the Earth to the sun is 1.5 times 10 to the 11 meters. Well, the first thing we need to know is how long is it going to take them to get to us? Well, if I measure that time from the Earth frame, from the sidewalk frame, all I have to do is take the distance traveled divided by the speed at which they're going. And this is physics 105 stuff. If it's 400 miles to Denver and I'm going 50 miles an hour, it's going to take me 8 hours to get to Denver. That's all it is, okay? The distance divided by the speed. And that gives me 882 seconds in the Earth frame. Now you'd be tempted to say, oh, well, that's about the same as the half-life of these neutrons. So I guess that if I started with 1,000 of them, half of them would still be neutrons. I should have 500. But that would be wrong, because these neutrons are moving really, really fast, about half the speed of light. And that means that their internal clock is running slow. Their aging clock, the clock that's telling them, oh, it's time to decay. Okay, so let's see how slow it's going. If I look at that velocity relative to the speed of light, it's just a little bit over half of the speed of light. And when I put that into my relativistic factor and multiply by the time that it takes on Earth for a neutron to decay, I find that it only takes 729 seconds in their frame of reference as they're moving very fast. And that, you see, is less than a half-life, less than one half-life. And so now when I calculate my M factor, how many half-lives do I have? I don't get one, I get something less than one. But that gives us a challenge. How do I calculate 2 to the m when m's not an integer? When m is 5, I know I just take 2 times 2 times 2 times 2 times 2. Well, what do I do when m is 0.827? Well, back before calculators, it was a little more complicated. But for you, if you get your calculator out right now, okay? And we give these instructions in our textbook, but you should have a button on your calculator that is y to the x. Okay? And so if I wanted to calculate 2 to the 0.827 power, I would type in 2, and then I would type in y to the x, and then I would type in 0.827, and then I would hit the equal button. And that is going to give you on your display 1.77. And so then I would take that 1.77, and
Whoa.
I started with 1,000 neutrons. I'm going to have 564 left over. Okay? Check that your neighbor understood that exercise.
So, yeah, so true. So yet again,
Okay.
but.
Um,
So,
I ran out of my heart medicine this morning, and I am just as dizzy as all get out. So we are ending the lecture for right now. So go somewhere else so I can lay down. Old people, what you gonna do? I'll be okay. I almost never think around.
I don't know.